Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. And in today's video, I'll be talking about binary logistic regression model. But even before I kickstart the process of building a logistic regression model using IBM SPSS, I request all of you to like, share, subscribe, and press the bell icon. What exactly is binary logistic regression model? We will explore this, but even before we get started with the codes and such things, let me give you a high-level perspective of binary logistic regression model. Firstly, it is a supervised learning technique. I repeat, it's a supervised learning technique. It is very similar to a linear regression model. Then you may ask me, what is the difference between linear regression model and a binary logistic regression model? The operative word when I say binary logistic regression model is binary. So binary logistic regression model is well suited when you want to model a dichotomous dependent variable. And thirdly, it is part of what is called as generalized linear models. So three important points: supervised learning technique. It is very similar to a linear regression model. It is well suited when you want to model a dichotomous dependent variable. And thirdly, it is part of what is described as generalized linear models. To explore binary logistic regression model, I will be using a case study. This is called as a bank loan case study. Here, we have a hypothetical person by the name Mr. Rajesh. He is working as a loan officer at a bank, and he wants to be able to identify the typical characteristics that are indicative of people who are likely to default on loans. And he wants to use those characteristics to identify good and bad credit risks. So this is a typical problem of credit risk analysis. We are interested in identifying the characteristics of those people which are indicative of a person being a bad credit risk. Now, with this background, what I'll do is I will jump to IBM SPSS. What you're seeing in front of you is IBM SPSS. Right now, you can see a blank screen because I have not used any data set. Let me quickly populate a data set. To access a data set, let me click on the file menu. I will move to recently used data. And what happens here is that IBM SPSS displays 10 recently used files. I'll go to the very first one. It says bank loan file. Let me select this particular file. You can see here what IBM SPSS does is it displays the entire data set of the customers. What we have here is historical data of customers who were part of the bank. You can see here we are given data about customer's age, his education level, the number of years that he has been with the current employer, the number of years that he has spent in the current address, what's his income. These are some of the variables that I have. And when I scroll to the right side, what do you see? You are also given information about his income. In fact, we are given information about his household income. Then the next three variables are very interesting because these are derived variables. The first of the variable is what is called as debt to income ratio. We are using debt in the numerator and we are taking income as the denominator and we are expressing this as a percentage. This will tell me what percentage of his income is under debt. Secondly, the variable credit debt, right? This is a variable which talks about credit card debt in 1,000. The next variable is other debt, again measured in 1,000. And the last variable is the most important variable because this is going to be my dependent variable. As you can see here, yes or no. The variable heading is default. The first person has defaulted on his payment. The second person is a non-defaulter, therefore he is being flagged as no. Third customer again is a non-defaulter. Fourth customer is a non-defaulter. Fifth customer is a defaulter. I'm interested in the yes category because this is indicative of a person being a defaulter. One very interesting thing to observe here is that you have two outcomes, yes or no. So whenever we want to model a binary outcome variable, we can use binary logistic regression model. So you may ask me, why am I not using linear regression model? When you look at this particular variable, this is not a scale variable. It is not a variable like income or experience or any thing of that sort. Here, I have got only two outcomes, yes or no. Since I've got only two outcomes, or only binary outcomes, this is the reason as to why we will be using the binary logistic regression model. So this is the outcome variable. The rest of the variables, that is the 8 variables, are my input variables. So to kickstart the process of binary logistic regression model, one question that we have to ask is, how do I execute a binary logistic regression model? To do this, let me click on the Analyze menu. SPSS displays a whole lot of options. I will move straight to the option which is called as regression. Now, the moment I click on regression, there is a whole lot of options that it will again display under the regression option, because you can do a linear regression model, binary logistic regression model, multinomial logistic regression model. What I will choose is the 5th option from the top. You can see here, I've gone to Analyze a regression, and within regression, I have chosen the option binary logistic regression. Let me click on this particular option. You can see here a new dialog box pops up. This is called as the logistic regression dialog box. In the canvas on the left-hand side, I have all the variables listed which are present in the data set. And in the canvas to the right side, you can see SPSS is asking me to specify the dependent variable as well as the covariates. Dependent variable, we are very, very clear. This is whether a customer has previously defaulted or not. So I'll be choosing the last variable, which has only 2 outcomes as the dependent variable. I will select all the other variables and push it as my covariates. So let me make this very clear. Dependent variable should have only 2 categories. We cannot have more than 2 categories because we are using binary logistic regression model. And the covariates can be all your demographic variables as well as the debt related variables. When you look at the right side, you have a lot of interesting options. You have a button for categorical, save, options, style, and bootstrap. I will not be generating any bootstrap replicates and such things. Let me choose the option categorical, which is the very first button at the top right-hand side. Now, is there anything useful? I can specify the categorical covariates and I can change the contrast. So I'm not interested in this, so I'll ignore this. What am I interested in is the option which is called as Save tab. Let me click on Save. Here, within Save, you can save a lot of additional columns, but I will choose 2 variables, save the probabilities as well as the group membership. So what this does is, in my data editor window of SPSS, it will create 2 columns, which will indicate what is the model predicted category. It will also tell me what is the propensity with which the model is estimating whether a person will default or not. So I'm interested in these 2 variables, predicted probabilities and group membership. I'll choose the option continue. I've got the next option, which is called as Options tab. Let me click on the Options tab. Here you can see a new dialog box pops up. I will choose something very interesting here, which is called as Hosmer Lemeshow Goodness of Fit. I repeat, this is called as Hosmer Lemeshow Goodness of Fit measure. So let me choose this and say continue. So what I've done here is to save 2 new variables and then choose Hosmer Lemeshow's Goodness of Fit. Now, with these selections, I am ready. So default is my dependent variable. All the other demographic variables I have chosen as the covariates. With this, let me click on the OK button. As you can see here, in a span of a few seconds, logistic regression throws a lot of output. But what I'll do at this stage is, even before I quickly interpret some of the results, I would like to sort of draw your attention to 2 or 3 points. So let me just quickly go to the output of logistic regression model. There are 3 or 4 important concepts which I would like to impress upon you. First one is what is called as the Hosmer Lemeshow test. What is this Hosmer Lemeshow test? Hosmer Lemeshow test is a goodness of fit measure. And if the Hosmer Lemeshow statistic indicates a poor fit if the significance level is less than 0.05. This is a very important point. When you look at the p-value for the Hosmer Lemeshow test, and if the p-value is smaller than 0.05, what does this mean? It means that there is a poor fit. So what we expect if we were to observe a good fit is for the p-value to be bigger than 0.05. So in binary logistic regression model, we check the Hosmer Lemeshow goodness of fit measure. This is the first thing that we need to keep in mind. The second important point here is about what is called as odds ratio. Now, in the case of linear regression, the beta coefficients are pretty straightforward to interpret. In the case of logistic regression model, it is not so easy for us to interpret the beta coefficients. This is where we look at what is called as the odds ratio. SPSS computes what is called as exponential of beta, which is popularly referred to as odds ratio. So you may ask me what exactly is the odds ratio. In the context of default, the way we can interpret the odds ratio is to simply say odds ratio represents the ratio change in the odds of default for a 1 unit change in the predictor. If you increase the predictor by 1 unit, what is the odds of default? That is what odds ratio tells us. Here, we have to be aware because there are 3 cases. The first case is when the odds ratio is greater than 1. Second case is the odds ratio is less than 1. And the third case is the odds being exactly equal to 1. Let's explore the first case. What happens when the odds ratio is greater than 1? If the odds ratio is greater than 1, the odds of default are increased. Very important point. When you look at the exponential of beta column, which we will explore in a couple of moments, if the odds ratio is higher than 1, it means that the odds of default are increased. Let's look at case 2, exactly opposite of case 1. What if you get the odds ratio less than 1? It simply means that the odds of default are decreased. And lastly, that is case 3, that is if the odds is exactly equal to 1, how do we interpret it? If the odds is exactly equal to 1, it simply means that the odds are unchanged. So odds ratio is very, very useful. It's a popular interview question as well. The third point which I would like to emphasize here is about pseudo R-squared statistics. Very important. They're called as pseudo. The word pseudo means false, which means that these are not the real R-square. These are pseudo R-square. So a couple of points here. The R-square statistic, which measures the variability in the dependent variable, that is explained by a linear regression model, cannot be computed for a logistic regression model. This is very important. Our coefficient of determination metric cannot be computed for a logistic regression model. Hence, what we do is we come up with what is called as pseudo R-square statistics, and they are designed to have similar properties as that of the true R-square statistic. So this is what I had when it comes to important concepts like Hosmer Lemeshow test, odds ratio, and pseudo R-square statistics. With this understanding, let us now explore the output produced by the logistic regression model on predicting defaulters. You can see here, we have what is called as the model summary statistic. The model summary statistic reports 3 important items here, what is called as -2 log likelihood, Then it also reports what is called as Cox and Snell R square. Very important. It reports Cox and Snell R square. And lastly, it reports what is called as Nagelkerke R square. Now, what I'll do is I'll just double click on the model summary output, select Cox and Snell R square, right click on this and choose the very first option which says, what is this? You can see here, SPSS is very, very user friendly. It gives you a description of what is this Cox and Snell R square. As you can read from the description, this is a generalized coefficient of determination. It is used to estimate the proportion of variance in the dependent variable, which is explained by the predictor variables. The Cox and Snell R square is based on the log likelihood for the model compared to the log likelihood for the baseline model. So this is a form of pseudo R square. The Nagelkerke R square again is what is called as a pseudo R square measure. This is derived from the Cox and Snell R square itself. There's another form of R square which is called as McFadden's R square. Now, we don't give too much of importance to R square in the case of logistic regression model, because this is at the end of the day a pseudo R square. This is not the genuine R square. So you may ask me, how do you evaluate the quality of the model? We have built a model. We have to assess whether or not this model is good or bad. Excuse me. So even before I answer this question, let us explore the Hosmer and Lemeshow test. Now, if you look at the chi-square value, SPSS displays a chi-square value of 8.039 and a degrees of freedom of 8. But interestingly, when you look at the significance level, it is 0.430, which is greater than 0.05. I repeat, 0.430 is greater than 0.05. And hence, I fail to reject my null hypothesis and conclude that the model fits the data well. Had this number been less than 0.05, then I could have concluded by saying that the model does not fit the data well. But remember, if the significance level is bigger than 0.05, our inference is that the model fits the data well. It's a good sign. To explore the quality of the model further, we have what is called as classification table. Sometimes it's also called as confusion matrix. Now you can see here, it's a 2x2 matrix. Along the row, SPSS says observed category. What is this observed category? In the last column in the data editor window, you saw the distribution of the number of defaulters. This observed category is split into two groups, no and yes. Some of them are non-defaulters, others are defaulters. Now, if you look at the column, you can see SPSS says predicted. Question is, predicted by whom? Predicted by the logistic regression model that we have just now built. So we have two important things here. One is the actual category. Second one is the predicted category, predicted by the logistic regression model. So you can see here, no actual category is no, predicted category is also no. So when the actual matches the prediction, it is a correct classification. So there are 472 non-defaulters that have been correctly predicted as non-defaulters by the logistic regression model. So you may want to know what is the percentage of accuracy when you are predicting non-defaulters. Please take a look at this number 91.3, and the heading here is percentage correct. So in identifying non-defaulters, my model is doing a fantastic job because it is telling me that 91 out of 100 times non-defaulters, 91 out of 100 non-defaulters have been correctly predicted as non-defaulters. So this is the true negative. Now look at this number 45. What does that mean? That simply means that there are 45 non-defaulters whom the model has misclassified as defaulters. Please look at this. Along the row, we have no. and the predicted category is yes. So 45 non-defaulters have been misclassified as defaulters. So that's how you interpret the first two numbers. Let's interpret the number 90 and 93 respectively. Now, when you look at this number 90, let's pay attention to what is the row heading. It says yes. So the actual category is yes. The predicted category is no. What does this mean? This simply means that out of 183 defaulters, 90 defaulters have been misclassified as non-defaulters. I repeat, out of 183, how do I arrive at this number 183? 90 plus 93 is simply 183. Out of 183 defaulters, my model has incorrectly classified 90 out of these people. Now look at this number 93. This represents correct classification. What does this mean? This simply means that out of 183 defaulters, my model has been able to classify 93 of these 183 defaulters as defaulters. So 93 is the correct classification. So diagonal elements are always the correct classification. Off diagonal elements are the misclassification. I repeat, diagonal elements from the top are the correct classification. So when the actual category is no and the model has predicted it as yes, my apologies, when the actual category is no and the model has predicted it as no, it is a correct classification. Similarly, when the actual category is yes and the model has predicted it to be yes, that again is a correct classification. So when you look at this number 50.8, which is a small number, which means that in predicting defaulters, my model is right only 50% of the times, which is not a good sign, because ideally speaking, we expect the model to get at least 70% accuracy. So this is a small number, 50.8. Now you may ask me what do we do because we have got only 50%? We may have to explore other models like support vector machine or a decision tree model or a neural network or any of the other classification schemes can be explored. Now, when you look at the overall percentage of accuracy, it says 80.7. So at an overall level, my model is doing a good job of explaining 80% of the cases. Now, these numbers, these four numbers, sort of tend to confuse people. So what I'll do is to interpret these numbers. Let me just take a few sample cases from the data and interpret it for you so that we are very, very clear as to what we're talking about. So this is the data set that we had. Very, very interestingly, if you recall, this is the actual category of default. Now you can see here, since I saved two columns, there are two additional columns that have been created. The first column is the probability score, and probability always lies between 0 and 1. So if the probability score is greater than 0.05, in fact, I should say 0.50, my apologies. If the probability score is greater than 0.50, that person will be classified as a defaulter. So this is the predicted category and this is the actual category. So this column PGR_1 is nothing but the predicted group membership. So how do we read this number? So when you look at the first customer, there is a 0.73. The predicted value is 0.73. So we can say that there is a 73% chance that he is going to be defaulting. So 73% is greater than 50%. So we are taking 50% as the benchmark. If the predicted category, if the predicted probability is greater than 50%, we will be calling him as a defaulter. If the predicted probability is less than 50%, we will be assigning him as a non-defaulter. So 73% is clearly greater than 50%. Therefore, we'll be calling the first customer as a defaulter. Look at the second number. It is 0.14. It is 14% only, which is very, very less. 14% is less than 50%. So we will be calling him as a non-defaulter. Look at the next category, 0.007, which means there is less than 1% chance that he will default. So we are calling him as a non-defaulter. There is only a 1% chance of him being a defaulter, which is very, very less. So we'll call him as a non-defaulter. Look at this chap here, the fifth guy, it is 0.76, which is greater than 50%. So there's a 76% chance that he is going to default. Since 76% is greater than 50%, I will be calling him as a defaulter. So this is the predicted category, and this is the actual category. So actual versus predicted. Let's examine the first person. Actual category is yes. Predicted category is yes. So when the actual matches the predicted category, we can go ahead and say that this is the correct classification. Look at the second category, no and no, which means this is the second individual has been correctly classified. Third customer, no and no. Actual is no, predicted is also no, which is the correct classification. Fourth is a good classification because it is no versus no. Fifth one is yes versus yes. And therefore, you can call this as a correct classification. There may be a few misclassifications as well. Look at the 10th individual. When you look at the 10th customer, he is actually a non-defaulter, but the model that we have built is calling him as a defaulter. So actual category is non-defaulter, predicted category is defaulter. This is a incorrect classification. This is a misclassification. A simple cross tabulation between these two columns should give you the confusion matrix. I repeat, a simple cross tabulation between the actual category and the predicted category should give you the confusion matrix. Now, even before I just show you how the cross tabulation and such things work, what I'll do is I'll just go back to the output of logistic regression model and explain the parameter estimate table. You can see here, it says variables in the equation. Very important. It says variables in the equation. All these are the independent variables that I had entered. And the last entry corresponds to the constant term here. This is the constant term or the beta naught term here. Age, level of education, years with the current employer, all these are the independent variables. What SPSS does is it reports 6 columns. The beta coefficients, then we have the standard error. This is the column for standard error. And then you have the Wald statistic, very important Wald statistic. Now you might want to know what is a Wald statistic. It is simply the ratio between beta and the square of the standard error. So if you just take beta divided by square of the standard error, you should be able to get 3.924. You also have the degrees of freedom and the significance level. Now, as I mentioned earlier, it is not very easy or straightforward to interpret the beta coefficients in the case of logistic regression model. Excuse me. And therefore, we look at what is called as exponential of beta or what is called as the odds. Now, how do we obtain exponential of beta? Just by passing this number 0.034 within the exponential function, we will be able to get the exponential of beta. Now, if you are a SPSS user and you want to look at the explanation, you can just double click on exponential of beta, select this and simply say, what's this? And SPSS gives the explanation for what is the odds. You can see here, E or 2.7128. My apologies, E or 2.718 raised to the value of regression coefficient. This is the value by which the odds of the event change when the ith independent variable increases by 1 unit. Now, let us try to interpret what is the odds ratio for age. You can see here, corresponding to age, we have the odds ratio value of 1.035. Question is this number greater than 1 or is it less than 1? Please ask this question of yourself. Is exponential of beta bigger than 1 or smaller than 1? You can clearly see here that 1.035 is a number which is greater than 1. So it simply means that if age increases by 1 year, then the odds of default increases by 3%. Right? Now, this is for age when the number is greater than 1. You can make better sense of this when you look at the debt related variables. Remember, the last three variables all talk about debt. Now, let me just interpret this particular variable, debt to income ratio. And the odds ratio is 1.07. How do we interpret this? It simply means that if debt to income ratio increases by 1%, odds of default increases by 7%. I repeat, if debt to income ratio increases by 1 unit, then the odds of default increases by 7%. It makes a lot of business sense as well, because if a customer's debt builds up, obviously there's a higher odds of him defaulting. The same argument can be made for credit card debt in 1,000. Look at this number. This is 1.86, which indicates that if the credit card debt in 1,000 goes up by 1 unit, then the odds of default increases by 86%. This is a very, very big number. This is how you can interpret any number which is greater than 1. So you may ask me, what about those numbers which are smaller than 1? For example, 0.772 or 0.900 or 0.991. How do we interpret these values? Let me just give you one example of 0.772. This is the odds ratio value for years with current employer. I repeat, so this is the odds value for years with current employer. We are getting a value of 0.772. What does this mean? It simply means that the odds of default, the odds of default for a variable, the odds of default for a person who has been employed at their current job for 2 years are 0.77 times the odds of default for a person who has been employed at their current job for 1 year, all other things being equal. I would like to repeat this point again. The odds of default for a person who has been employed at their current job for 2 years are 0.77 times the odds of default for a person who has been employed at their current job for 1 year, all other things being equal. So this is how we can interpret the odds ratio value. One additional thing that I'd like to draw your attention to is the significance value. SPSS reports the significance value for each and every column. How do we interpret the significance value? If the p-value is less than 0.05, it simply means that the parameter is useful to the model. I repeat, if the p-value is smaller than 0.05, it means that that particular parameter is useful to the model. On the other hand, if the p-value is larger than 0.05, it means that that particular parameter is not useful to the model. So when you examine some of the significance value, look at level of education, 0.462, greater than 0.05, so not useful to the model. Let me look at the significance value for household income. It is 0.282, greater than 0.05, not useful for the model. If I scroll down, you can see other debt in 1,000, it is 0.418, greater than 0.05, and therefore it is not useful to the model. All the other variables you can see here, the p-value is less than 0.05. For example, age, the p-value is less than 0.05. Years with current employer, years at the current address. Then you can also look at debt to income ratio, credit card debt in 1,000, other debt, sorry, not other debt, but credit card debt in 1,000. These are variables wherein the p-value is less than 0.05. So very simple thumb rule. If the p-value is less than 0.05, it means that the parameter is useful to the model. If the p-value is greater than 0.05, it means that the parameter is not useful to the model. So this is how we can interpret the Hosmer Lemeshow Goodness of Fit measure. We then proceeded to look at the classification table or the confusion matrix. We looked at the variables in the model. I also explained about the model summary statistic. Before we conclude this, I'd like to revisit this point about classification table. You have the actual versus the predicted. So let me just open up the data editor window. You can see here, this is the actual and this is the predictor. What I'd like to do is I'll just do a simple cross tabulation between the actual and the predicted. I can use the analyze menu here, choose the second option here, which is called as the descriptive statistics. Within descriptive statistics, I will choose the fourth item, namely crosstabs. You can see here, it is asking me to specify the row variable as well as the column variable. Now, the first variable that I will be supplying is the actual category of default. This is the actual category that I'm supplying along the row. In the background, you can see here, this is the variable which I'm using. Now, along the column, what I'll do is I will supply the predicted category. This is the variable which I've highlighted at the backend for you. So I'm just looking at a simple cross tabulation between actual versus predicted. If you want, you can look at the percentages and such things. I want to keep it very simple. There's a simple cross tabulation between actual and predicted. Let me click on OK. You can see here, this is what you're getting. Are these numbers familiar? 472, 45, 90, and 93. So this is the output of the cross tabulation that we are getting. So let me just delete some of this output so that I can just impress upon you the classification table. This is the earlier classification table that we got based on the logistic regression model. And this is the output of the cross tabulation. Look at this 472, and this is 472, 45 and 45. Here we have 90, here we have 90, and this is 93, and this is 93. So this is the output of cross tabulation. What you're seeing here is nothing but the classification table. People also refer to this as the confusion matrix. It is simply a cross tabulation between the actual and the predicted. So with this, I've come to the end of today's video. In this video, we looked at binary logistic regression model. We looked at some of the model diagnostics. We can look at model summary statistics, especially the pseudo R-square. It could be Cox-Snell R-square. It could be McFadden's R-square. It could be Nagelkerk R-square. All these are basically pseudo R-square. We can also look at other important things like Hosmer and Lemeshow test. Then we proceeded to look at the confusion matrix. And finally, we looked at the parameter estimates table. In the parameter estimates table, the most important column there would be the odds ratio. How do we interpret the odds ratio? Just ask a simple question. Is it greater than 1 or is it less than 1? Greater than 1, the odds of default are increased. Less than 1, the odds of default are decreased. If the odds ratio equals 1, it means that the odds are unchanged. With this, I've come to the end of today's video. If you have liked this video, I request you to I request you to subscribe to my channel and hit the like button. Thank you very much for watching this video. Have a great day.